There is a sound in a commercial cockpit that changes everything the moment it starts. A continuous tone, a red light, 3 letters on the screen, the sign for a fire, not a warning that something might be wrong, a confirmation that something already is. The engine behind you is on fire. What happens next? In the cockpit, in the nacelle, inside the engine itself, takes less than 40 seconds from the moment that alarm activates to the moment the fire suppression system has done everything it was designed to do. The pilots are part of that sequence, but they are not the beginning of it. The beginning happened before any human being on that aircraft knew there was a fire at all, because the jet engine, the same engine that passengers have flown behind for decades without thinking twice, was not designed to prevent fires. It was designed to survive them. Every fire zone defined, every sensor positioned, every valve ready to close, every bottle of suppressant armed. The engineering that makes a jet engine fire survivable was built into the aircraft before it ever left the factory. This is how it works. In a suppression system at all, you first have to understand what temperature conditions a jet engine creates by design, and how many flammable substances exist in the same physical space as those conditions. The combustion chamber of a modern turbofan engine operates at gas temperatures between 1,400 and 1,700 degrees Celsius. That is hotter than molten steel. The high-pressure turbine immediately behind the combustion chamber operates in gas that exceeds the melting point of the blades themselves, managed only by cooling air bled through microscopic internal channels in each blade. The entire rear section of the engine core is, in thermal terms, one of the most extreme environments created by any machine in commercial service. Running through the structure surrounding that hot core, the nacelle, are fuel lines carrying jet fuel at high pressure, hydraulic lines carrying hydraulic fluid at high pressure, bleed air ducts carrying compressed air at temperatures high enough to ignite fluid on contact, electrical wiring, lubrication oil lines, fuel, hydraulic fluid, oil, all of them flammable. All of them within meters of surfaces operating at temperatures far exceeding their ignition points. This is not a design flaw. It is an unavoidable physical consequence of putting a combustion machine inside an aircraft that also needs fuel, hydraulics, and lubrication to function. The engineers who designed the first jet airliners did not look at this arrangement and conclude that fire was something to prevent. They concluded that fire was something to contain, detect, and suppress, because the conditions for it would always be present. Aviation regulations, specifically FAR Part 25, Section 25.1181, define fire zones on any turbine-powered aircraft. A fire zone is any region that contains a concentration of flammable fluid lines, ignition sources, and surfaces hot enough to cause ignition, and that requires fire detection and suppression equipment to be installed. On a modern turbofan installation, the primary fire zone is the space between the engine core and the inner surface of the nacelle cowling. This annular cavity, shaped like a hollow cylinder around the engine, is where the fuel lines run from the pylon to the fuel nozzles, where the hydraulic lines run to the thrust reverser actuators, where the engine oil lines run to the gearbox, and where all of these lines are exposed to the thermal environment produced by the engine they're servicing. Separating this fire zone from the aircraft's wing and pylon structure is a titanium firewall, not steel. Titanium, because titanium maintains its structural integrity at temperatures that would cause steel to lose load-bearing capacity, and because in an engine fire, structural integrity of the firewall is not optional. If the firewall fails, the fire moves from the engine into the aircraft structure. That is the failure mode that makes an engine fire catastrophic rather than survivable. The firewall exists to make that transition physically impossible for a specified period of time. Engine fires on commercial aircraft fall into 4 primary categories, and understanding them explains why the detection system is designed the way it is. The most common is a fuel leak onto a hot surface. Fuel lines in the nacelle operate under pressure. A chafed line, a failed seal, a cracked fitting. Any of these can allow pressurized fuel to spray onto surfaces operating at hundreds of degrees. Jet fuel has an auto-ignition temperature of approximately 220 degrees Celsius. The external surfaces of the engine core operate well above that. Contact between sprayed fuel and a hot engine surface produces ignition without any spark. The second cause is hydraulic fluid leak. Hydraulic fluid, skydrol, or similar aviation-grade fluid, is less flammable than jet fuel, but still combustible at elevated temperatures. A failed hydraulic actuator on the thrust reverser system, located inside the nacelle, can release fluid into the fire zone in the same way. The third cause is bleed air duct failure. High-pressure bleed air, extracted from the engine compressor stages, is routed through the nacelle to supply the aircraft's pneumatic systems. That air is compressed and hot. Temperatures at the bleed port can exceed 200 degrees Celsius. A cracked duct allows this air to escape at high velocity into the fire zone, heating surrounding surfaces and potentially igniting any fluid present. The fourth is an internal engine failure, a turbine blade fracture, or a bearing failure that allows internal oil or fuel to escape into the core in ways the engine's internal seals are not designed to manage. These are rarer, but produce the most intense fire conditions because they occur inside the engine rather than around it. In all four cases, what the fire detection system is looking for is the same thing: a sustained rise in temperature inside the fire zone above the threshold that indicates combustion is occurring, not merely engine operation. The fire detection system inside a jet engine nacelle does not detect flame. It does not look for smoke. It does not measure the visual presence of combustion. It measures temperature. Specifically, it measures temperature continuously around the entire circumference of the fire zone, using a sensing element that changes its electrical behavior when it exceeds a defined temperature threshold. The most common type in commercial use is the continuous loop detector. A sensing element, a metal tube, typically Inconel, roughly the diameter of a pencil, runs from one end of the fire zone to the other, wound around the fire zone in a path that ensures no area larger than a few centimeters goes unmonitored. Inside the tube is a central wire, separated from the outer tube by a packing of salt-based eutectic material, a mixture chosen because it remains electrically resistive at normal temperatures, but becomes conductive when heated above a specified threshold. Typically, that threshold is set between 200 and 400 degrees Celsius, depending on its location in the nacelle. Under normal conditions, the salt packing has high electrical resistance. The signal between the inner wire and the outer tube is below the threshold that triggers an alarm. The system monitors this resistance continuously. When a fire begins, when temperature in any section of the fire zone rises above the detection threshold, the salt in that section of the loop liquefies and becomes conductive. The resistance drops. A signal is sent to the fire warning computer. This happens at the speed of thermal conduction. A fire that has been burning for 2 to 4 seconds will have raised the local temperature enough to trigger detection. The system does not wait for smoke to reach a detector. It does not wait for flame to be visible. It responds to the thermal signature of combustion as it develops. Every commercial jet engine carries 2 of these sensing loops, running parallel paths around the same fire zone. This is the dual loop design. Both loops monitor the same space. The fire warning computer can be configured to alarm if either loop triggers, which maximizes sensitivity, or if both loops agree, which minimizes false alarms. Most modern installations use a dual loop single fault logic. Either loop can trigger the alarm under normal conditions, but if one loop has developed a fault, the system automatically requires both to agree before alarming. False fire warnings are operationally disruptive, and the dual-loop architecture was designed to make them vanishingly rare without compromising detection sensitivity. When the detection threshold is exceeded, the fire warning computer activates simultaneously. A continuous fire bell in the cockpit, a master warning light, and the engine fire handle light. A red illuminated T-shaped handle on the overhead panel or thrust lever panel, depending on aircraft type. On aircraft with ECAM or ICAS displays, a fire message appears with the affected engine identified and the required crew action displayed. The bell continues. The handle light continues. The system is designed to be impossible to miss and impossible to misidentify. Both pilots can see which engine the handle corresponds to. The procedure from that point is a memory item, executed without reference to a checklist for the first 3 steps, because a fire demands immediate action, and reaching for a checklist before responding costs time the aircraft may not have. The first memory item is a single physical action. Pull the fire handle. The fire handle is not a simple switch. Pulling it does not merely alert someone to a fire. Pulling it arms a suppression bottle, and it does 4 other things simultaneously. 5 actions completed by a single mechanical pull in the time it takes to extend your arm. 1. The high-pressure fuel shutoff valve closes. Fuel stops flowing to the engine. Without a continuous fuel supply, combustion inside the engine core will cease, but more importantly, the fuel line pressure in the nacelle drops, reducing the fuel available to feed an external fire. 2. The bleed air valve closes. The flow of hot compressed air from the engine into the aircraft's pneumatic systems is cut. This prevents fire from propagating through the bleed air ducting into the aircraft structure and removes the high-temperature air source that can sustain combustion in the fire zone. 3. The hydraulic firewall shutoff valve closes. Hydraulic fluid stops flowing through the lines in the nacelle. The hydraulic fluid that powers the thrust reverser and other nacelle-mounted actuators is isolated from the fire zone. A flammable fluid source is removed. 4. Electrical power to the engine components is isolated. Generators driven by the engine are taken offline. Electrical arcing as an ignition source is eliminated. 5. The halon suppression bottle is armed. The agent is now ready to be discharged into the fire zone on command. All 5 of those actions happen simultaneously. 1 mechanical pull, 1/4 second of movement, and the engine has been isolated from every fuel source, every flammable fluid source, every electrical system, and the suppression agent is ready to discharge. The engine is not being shut down as a response to the fire. It is being sealed off from the aircraft so that whatever is burning inside the nacelle burns with a diminishing supply of everything fire needs. With the fire handle pulled and the bottle armed, the pilot presses the fire handle inward, rotating or pressing it depending on the aircraft type, to discharge the halon suppression agent into the fire zone. Halon 1,301, bromotrifluoromethane, is the agent used in engine fire suppression on most commercial aircraft. It is not a cooling agent. It does not smother the fire by removing oxygen, though it does reduce oxygen concentration slightly. Its primary mechanism is chemical. Halon molecules interrupt the chain reaction of combustion at the molecular level, preventing the fuel-oxygen reaction from sustaining itself. It is extraordinarily effective in enclosed spaces at low concentrations. A 5% concentration of halon in the fire zone is sufficient to suppress most hydrocarbon fires within seconds. The halon bottle, a pressurized steel cylinder typically mounted in the pylon structure, contains enough agent to fill the fire zone once. That is the first bottle. Every commercial twin-engine aircraft certified for ETOPS, extended operations over water, carries a second bottle. The second bottle is the crossfeed. It can be discharged into either engine's fire zone from the opposite engine's supply. After the first bottle is discharged, if the fire warning continues for 30 seconds, the crew discharges the second bottle. If the second bottle is discharged and the fire warning continues, if both bottles have been expended and the nacelle temperature has not dropped below the detection threshold, the fire is considered uncontrollable, and the aircraft diverts to the nearest suitable airport immediately. This scenario is rare. In most cases, the first bottle is sufficient. In most cases, the fire warning has already ceased before the second bottle is ever considered. On September 8, 2015, British Airways Flight 2276 was preparing to depart Las Vegas McCarran International Airport, bound for London Gatwick. The aircraft was a Boeing 777-200, powered by 2 GE90-85B engines. At 16:13 local time, the crew pushed the thrust levers forward for takeoff. During the takeoff roll, at approximately 80 knots, a high-pressure fuel manifold in the left engine failed. Pressurized fuel at high flow rate was released into the engine nacelle's fire zone. Contact with the hot engine surfaces caused immediate ignition. The fire detection loop registered the temperature rise. The fire warning activated in the cockpit within approximately 3 seconds of ignition. The crew rejected the takeoff. At 80 knots, the aircraft had significant runway remaining. Auto brakes were applied, thrust reversers deployed, and the aircraft decelerated to a stop. As the aircraft slowed, the left engine fire handle was pulled. The 5 simultaneous actions executed: fuel shutoff, bleed air closure, hydraulic isolation, electrical isolation, halon armed. The first halon bottle was discharged. The fire in the nacelle had, by the time the aircraft stopped, grown beyond what the first bottle could immediately suppress. The fuel that had sprayed into the fire zone before the shutoff valve closed had pooled on internal surfaces and continued to burn. Passengers could see flames from windows over the left wing. The fire warning continued. The second bottle was discharged. The fire warning light extinguished. All 172 people on board evacuated using the emergency slides. 27 people suffered minor injuries during the evacuation: bruises, abrasions from the slides. The aircraft sustained significant damage to the left engine and nacelle. One person returned to the aircraft to retrieve luggage and was fined for it. The left engine GE90-85B was destroyed. The titanium firewall between the nacelle fire zone and the pylon held throughout. The wing structure was not penetrated. The fuel tanks were not compromised. The fire did not reach the aircraft beyond the boundaries it was designed not to cross. The detection loop caught the fire in 3 seconds. The handle isolated the engine in the time it takes to pull an arm. The halon suppressed the fire before structural failure could occur. The firewall held the margin that allowed all of that to work. The survivability of the BA-2276 fire and every other contained engine fire in the commercial aviation record is not accidental. It is the product of a specific certification standard that defines how long an aircraft engine must be able to contain a fire before structural failure is permitted. FAR 25.1181 requires that any component in a fire zone that is not protected by a firewall must be capable of withstanding a fire without failure for the period required by the fire extinguishing system to suppress it. For structural firewalls specifically, FAA fire test standards require that a certified firewall must contain a 2000 degrees Fahrenheit, 1093 degrees Celsius flame without allowing flame penetration for 15 minutes. 15 minutes is not the expected duration of a suppressed engine fire. It is the duration the firewall must survive if every other system in the suppression sequence fails. If the detection loop fails, if the halon does not suppress the fire, if the crew cannot act, if the aircraft cannot be landed immediately. The 15-minute standard is the worst-case margin built into the material itself. In normal operations, the time from fire detection to halon discharge is under 60 seconds. The time from halon discharge to fire suppression, in cases where suppression is successful, is between 10 and 30 seconds. The 15-minute firewall standard sits behind all of that as a physical guarantee that even if everything else in the sequence fails, the structure gives the aircraft enough time to land. Since the modern dual-loop detection system and halon suppression became standard on commercial jet aircraft in the late 1960s and early 1970s, no commercial passenger aircraft has been destroyed by an engine fire that began in the nacelle fire zone and was not detected by the onboard system. That is not a claim that engine fires have not occurred. They have, on thousands of flights in the decades since. It is a claim that the detection, suppression, and containment system, the sensing loops, the fire handle, the halon bottles, the titanium firewall, the certification requirements behind all of it, has caught and contained every one of those fires before they reach the aircraft structure. The alarm you hear in the cabin is alarming because that is what it is designed to be. Impossible to miss, impossible to misidentify, immediately actionable. What it is not is the signal that something has gone wrong, that the aircraft cannot handle. It is the signal that something has gone wrong that the aircraft has been handling automatically and precisely for the last several seconds, and that the crew is now being asked to confirm and complete a sequence that was already underway. 2 detection loops running the full circumference of the nacelle fire zone. a eutectic salt-sensing element that becomes conductive above its threshold temperature and sends a signal before any human being on that aircraft has seen or smelled anything. A fire warning computer that activates a bell, a master warning, and an illuminated handle simultaneously. A fire handle that closes the fuel shutoff valve, closes the bleed air valve, closes the hydraulic firewall valve, isolates electrical power, and arms the suppression bottle. All 5 actions, 1 pull. A titanium firewall certified to contain 1093 degrees Celsius for 15 minutes. A halon bottle that interrupts combustion chemistry at a 5% concentration, a second bottle in reserve. And a certification requirement that the engine must survive its own fire long enough for the system to suppress it. The detection loop catches the fire. The handle closes every supply the fire needs. The halon ends it. By the time you hear the alarm, the engineering has been working for several seconds already.